lion and the man. Okay. So we have a unit disk, and we have a lion in there, and there's a man in there. We're going to represent them with a point. The lion wants to catch the man and eat the man. The man wants to get away and not get eaten. So that's the goal for the man. They're going to have the exact same speed. So for the purpose of this talk, I'm going to assume that they both go in speed 1. They're going to be on the unit disk. All right, so what do you think? Can lion always catch the man, or can man always get away? Who thinks lion can always catch the man? Who thinks man can always get away forever? Less of you. Okay, it's I guess the rest is not sure. About half of the room is not sure. So let's do some intuition building. Okay, so it should be clear that if man is running directly away from the lion, the man cannot be caught, right? Because they're running at the same speed. But you can't keep doing that because man is going to hit the boundary of the disk. So eventually, at some point, man is going to have to turn. If man turns, though, the lion can adjust his trajectory just a little bit and close the gap just by a little bit. So really, the question comes down to can lion catch the man in finite time? So lion can always close the gap as long as man keeps turning, but that might take forever, right? Or maybe it happens in finite time. So when I first encountered this problem, I tried the simplest thing you could think of. Right? So the simplest thing you could think of is the greedy strategy for the lion. So what the lion is going to do is run full speed towards the man all the time. So I haven't figured out what the strategy for the man is. So what I'm going to do is I'm going to place the man on the border of the arena and go counterclockwise with speed 1. And let's see what happens to the position of the lion as the man goes in a circle. So some notation. So the man is going on the unit circle, going counterclockwise with speed 1, so cosine sine. And I'm going to put the x and y coordinate for the lion, I'm going to denote it with x and y. And the initial condition, we're just going to assume that the lion starts at the origin. Okay, so lion is always running towards the man. So the lion's velocity vector is pointing exactly towards the man. But I can't just use that as the velocity vector because I need to normalize it, right? He's running at speed 1. So I'm dividing by the length of the vector there. Okay, so this is going to give me a differential equation, the lion's position at time t. And plugging in the coordinates for the man, this is what I get. I have no idea how to solve this differential equation. So I asked MATLAB to solve it for me. So here's what I got. So it's a spiral. It's kind of hard to see with the resolution, but the lion keeps on running. So at least with the greedy strategy, it doesn't seem like lion can catch the man.
Does he definitely limit towards catching him?
Yeah. Definitely the distance goes to 0. It turns out the lion can be a little bit smarter. So here's a second strategy for the lion. Okay. I'm going to call this the radial lion strategy. So what the lion is going to try to do in this setting is that he's going to place himself between the origin and the man. And so as the man rotates on the boundary, lion's going to stay on this line segment connecting the origin of the man. And it doesn't take as far for lion to turn, right? So he can spend his extra speed kind of running towards the boundary. Does everybody get what I'm trying to say? Okay. So let's do the setup again. So the man is running counterclockwise again, speed 1. But this time, I'm gonna let the position of the line always be some function times cosine and sine. So the line is some radius away from the origin, and we can figure out if this gets to 1 or not. Okay, so I took derivative for the x and y. Product rule. I know that the speed for the line has to be 1, so I know this has to hold true. So this is going to give me a differential equation for the r. I plug it in, the derivative I got, and do a little bit of algebra. I'm going to skip through this because I know my talk is a little bit over 20 minutes. And you get a very reasonable differential equation. You could actually solve this not too much problem, so that the radius is going to be sine of t. Okay, so if I plug in sine of t into what I got for x and y, so I'm going to plug in sine of t for the r of t, this is what I get. It's kind of hard to see what this means, but if you use a trig identity, it traces out a circle. So this is what the path looks like. So as the line is running counterclockwise, the man is running counterclockwise, the line is also tracing out a circle, radius 1/2, and it hits exactly the northern end of the arena at time pi over 2. So line actually gets to the man in finite time, at least in this case. So the line says to the man, if you run counterclockwise, I'm going to catch you at the northern end of the arena. If you run clockwise, I'm going to get you at the southern end of the arena. If you change direction somewhere in between, I'm going to reflect my trajectory, so I'm going to stay on track. And if you ever slow down or stop, I could spend my extra speed running towards you, so I could actually get to, so the lion could get to the man quicker. So therefore, lion has the winning strategy. What do you think?
I think it's wrong.
You think it's wrong?
Yeah, it's too early.
You're exactly right, though. What's the Aryan line?
I don't know.
Find that number.
Right. So what else can he do?
Run in towards the center of the circle as well.
That's right. Yeah. This argument totally ignores the fact that man can actually run into the interior of the disk. So it seems counterintuitive, but man actually can do better if he steps into the disk and do something else. So let me show you exactly what man can do. Okay. So here's the man's escape strategy. All right. So for the rest, I'm going to assume the lion starts at the origin and man starts somewhere in the interior. I'm going to assume this without loss of generality. If man started at the boundary, he could at least take a step inside of the ring before the lion can get to the man. So this argument could generalize.
Will this be for arbitrary lion strategy now, or?
Yes. Yeah.
Okay.
Yes. Yeah. This will be for arbitrary. So you can be the judge. Okay. So what the man is going to do is he's going to run in a polygonal path, and I'm going to make some notation for this. So the original spot for the man, I'm going to call that M0. And after he runs some distance L1, he gets to the point M1, and M2 and M3 and so on. So at the corner of the polygon, I'm going to mark it with M sub or something. So that's what I'm going to denote. And the line segments between the terms, I'm going to denote it L1, L2, L3, and so on. Okay. All right. So the man's strategy is going to go like this. I'm going to define it inductively. So let's say at some step n, a man hasn't been caught yet. Okay, so he's gonna turn and check where the lion is. He's gonna draw an imaginary line between himself and the origin and see which side the lion is on. And what the man is gonna do is he's gonna run exactly perpendicular to, I can't use this very well. He's gonna run perpendicular to this line connecting the origin and the man in the direction away from the lion. So in this picture, the lion is sitting in this half plane. So man is gonna run that way. If the lion is on the other side, the man is gonna run this way. If lion is on the line segment itself, like the radial strategy, it actually doesn't matter which way the man runs, so it's both okay. And I claim that while he's running perpendicular from this line, he's not gonna get caught. Okay? Because for the man to get to the point m sub n plus 1, the shortest distance between that point and this half plane is exactly where man was. So since lion is somewhere away from that, he can't get to there in the same amount of time. Does that make sense what I'm saying? It's kind of hard to place the words there. Okay. And then he's going to run some distance L sub n plus 1. Okay. And then after he runs some distance, he's going to draw his imaginary line between himself and the origin and do the same thing again. He's going to start running in a perpendicular direction away from the lion if possible. If he's on the segment, he can choose whichever, it doesn't matter. Okay. So does this strategy work? So there's a couple things that I haven't justified yet, so let me try to convince you that this can be done. One issue is that it's not clear if this goes on forever. I haven't told you the distance he's running. I just said L sub n. If the sum of the distance the man is running is finite, then he runs out of the path that he's running on, and then he doesn't know what to do. Right? So for this strategy to make sense, I need the sum of the length he's running to be infinite, because he could be running forever. Does that make sense? Okay, so I need that to be true. There's another issue. I have to make sure that the man stays close enough to the origin. He doesn't escape the arena or hit the boundary. So that's another thing I need to check. So let's check it. So I'm going to denote the distance the man is from the origin with d sub n at step n. All right. So let's start from step 0. So at the beginning, he's gonna run upward, some distance L1. And when I run perpendicular, I kind of make this right triangle, right? From the origin to the man to the next point. Okay. The distance he runs is L1, and the distance from the origin, I denoted D1. I can compute exactly what the distance is with Pythagorean theorem. I could do this again. So on the step number 2, the man is running perpendicular from the line connecting origin to M1. I can point diagonally. I can make another right triangle. And I could use Pythagorean theorem again. You see the second right triangle there? Yeah. So D2 squared is going to be D1 squared plus L2 squared. But I already have a formula for D1 squared. So I'm going to substitute that in there. Okay. Is what I'm doing making sense? Okay. All right. So do this inductively. So after nth step, the distance, square of the distance from the origin is going to be 1/2 squared plus the square of the distance the man has been running so far. All right. So if you want the distance from the origin to be within 1, it's the same as saying it stays within the arena. I need this infinite series plus 1/4 to be less than or equal to 1. All right. So let me summarize the two conditions I need. I need the sum of the distances to be infinity, and sum of the square of the distances to be small enough. Okay. So there's actually many answers that I can pick here. One answer that would work is 1/πn. So sum of 1/πn is infinity. It's a constant times harmonic series. It's going out to be infinite. And the sum of the squared, I could pull the constant pi squared out here. Does anybody here know what the sum of this is? Yeah.
Pi squared over 6.
Yeah, totally. Pi squared
And the
over
next
6.
one is pi 4th over 90, and pi 4, pi to 6 over 945. But no one knows that one.
Do you study zeta function or something?
Yeah.
Yeah, awesome. Excellent. So it is pi squared over 6. So the pi squared cancels out. 1/2 squared plus 1/6 is less than or equal to 1. So he stays within that. If you don't know how to do this, you could actually make a very reasonable estimate of the integral. Still show that it's less than 1. It's not too difficult. Okay, so the conclusion, the man can run forever, and he's staying within the arena forever. The lion cannot catch the man in finite time.
But you can get really close.
Yeah. I don't recommend trying this at The lion will do it. Okay, so this is a puzzle that was made by Richard Rado in 1920s. He kind of spread it by word of mouth. And the radio lion strategy actually was accepted as the solution to the problem. So people actually didn't know that the man could get away at the beginning. After about 20 years or so, Abraham Biskovich found the error and had the correct solution. It's pretty cool that the puzzle wasn't solved for 20 years. And he flips the answer on his head, right? Pretty cool problem. Okay. And I don't know if you guys play video games, and I'm a gamer. And I did notice that Lion and Man, a version of Lion and Man, was a popular video game. It's a game called Mario Chase. It's a couple years old, and well, it's a game where up to 4 people are trying to catch Mario. So these are the 4 mushroom people that could be running, and the guy with the tablet, the Mario, has a top-down view, and he could be planning his path. Clearly, the people who are chasing are first-person view, so it's a little bit hard to detect which way Mario has been running. But you get some information. You get the distance to the Mario. It's a fun game. It's interesting how people play that. When they first play this game, most people start doing the greedy lion strategy. They run directly at the Mario. And if Mario doesn't get caught for 2.5 minutes, Mario gets to win. If the mushroom people wants to win, they really have to work together to kind of get around. This version of the Lion and Man problem, where you have a bounded region with several obstacles and multiple lions, this is actually an open problem. So do some math research.
So what about just 2 lions that aren't cooperating and no obstacles? Is that still open? Or is
Oh, no, actually, what's known is this. In 2 dimensions with 2 lions, lions can catch the man.
without cooperation?
I think there needs to be cooperation. Yeah, there has to be some kind of strategy together. So in fact, actually, this is a little bit more general than that. In n dimensions, so disk is a two-dimensional arena. So in n dimensions, in a bounded n-dimensional ball, n lions is enough to catch the man, but n-1 lion is not enough to catch the man. So more space requires more lions to catch the man. All right. And if you thought this problem was interesting, there's lots of problems like it. There's a lot of cool problems that come with this book. Strongly recommend.